Yeah, I'm David Krueger. Just a little bit about me. I've been concerned about sort of the social impact that AI might have and this idea that it might be an existential risk to humanity since about 2009. So actually before I even got into the field of AI in any serious way. And I've been studying deep learning since 2012. So I sort of was lucky enough to hear about the deep learning revolution right as it was kicking off from a Coursera course from Jeff Hinton. And about a year ago, I started my current position as an assistant professor here at Cambridge. And so what I'm doing now is building a research group that's focused on deep learning and also AI alignment and existential safety. And one thing I want to plug right now is that I am looking for postdocs. So if you're interested, please get in touch. Anyways, so this is going to be like two separate parts to this talk. So the first part is sort of about AI safety in broader sense. And the second part is going to be more focused on AI alignment and existential risk. So I want to start out with this picture. So this is kind of the sort of thing that got me really excited about deep learning. I mean, this and seeing a few of the examples that Jeff had of like it actually working, right? So back in 2012, we already saw AlexNet, that neural nets could like do a remarkably good job of classifying images. And there was also, maybe less known, what I found even more impressive was a demonstration of an RNN generating text, like one character at a time, and coming up with, its own new words and occasionally making something that looks sort of like linguistic sense. So anyways, I should have mentioned this as well, I did all of my graduate studies at Mila, the University of Montreal, so working with Joshua Bengio, Aaron Corville, Roland Marisik, and tons of other collaborators there. And that was really like the deep learning mecca at the time because Jeff Hinton and Jan LeCun had gone to industry around when I joined. And so Joshua and Mila was sort of the only place that you could still go in the early days of deep learning to study under experts in grad school. And I think Joshua probably did more than anyone else in terms of like popularizing deep learning at this time. And so here's a figure from one of his early papers sort of arguing, as he had been for a long time, even before 2012, that deep learning was the way and was the future. And the idea is, you start with some input image, and to the computer, this of course just looks like a bunch of numbers representing pixel values. And the idea is deep learning should allow you to learn this deep hierarchical distributed representation, and this should disentangle the underlying factors of variation in the data. And so as you sort of move up this neural network, you should get to higher and higher representations that might be looking at things like edges and object parts until eventually you have this very nice high-level representation that in this case might just say, oh, this is a picture of a man sitting, and he has curly hair and it looks like some sort of desert or scrubland in the background, this sort of stuff. And maybe we don't know what the right concepts are. Maybe they should roughly correspond to the things that we have words for. But the hope is that we could do all of this sort of automatically, maybe even unsupervised without any labels. And I want to ask the question, is this what deep learning is actually doing in practice? And I think the reality and the answer is unfortunately no. I mean, it might be doing something sort of similar, but it seems like it's clearly not learning, the concepts that things like man and sitting. It's learning some sort of weird alien concepts, and we can see that through a number of ways, but maybe most famously, notoriously, and obviously by looking at adversarial examples like this. And so there are these, as I'm sure most of you know, there are these like small perturbations that you can make to images to completely change what neural networks will predict about those images. And this is has been a remarkably enduring failure mode of these models. And so when we look at a representation learning system like a deep neural network, a very important question, I think, is it learning the right concepts? And as soon as you start to ask that question, I think, the questions just multiply. You have to ask, well, what does that even mean, actually? So like, what is a concept? Is a concept like a vector? Is it one component of the vector? How could we actually tell if it's learning the right concepts? I mean, it's generalizing well in distribution a lot of the time, but then maybe not out of distribution. It can actually be difficult and subtle to test the model in the right ways to reveal what exactly it does and doesn't understand, or sort of how it's looking at the world, what is generating its behavior. Maybe the problem isn't the models, maybe the problem is us. Maybe humans don't actually use the right concepts. Maybe our concepts are the ones that are broken, and actually AI systems are going to learn better concepts than us that are more predictive, although that doesn't seem to be the case so far for the most part. But who gets to decide which concepts are the right ones as well? Like, is it me? Is it you? Is it society? People have different ideas about what different concepts mean. So the whole abortion debate in the United States is largely about what counts as a human life. And you can ask, like, are our concepts actually sensible in the first place? Like, if you really dig down and try and like formalize what we mean by different concepts, a lot of the times it seems like they kind of slip through our fingers. And in philosophy, there's been a bunch of work on trying to answer these questions. And, you know, because it's philosophy, maybe we haven't made that much progress. Let me just turn on my laser pointer here. Yeah, so just as another example that I thought was also really interesting and sort of illuminating, there's a really recent paper by some folks at Cambridge, Tübingen, some other places, that was, I think, really directly trying to test this picture of disentangling factors of variation, and doing this by really kind of stacking the deck in favor of the neural networks. So saying, let's not, you know, worry about doing this unsupervised or doing this based on, you know, some label that is maybe only weakly indicative of what these underlying factors of variation are. Let's take data sets where we know what the underlying factors of variation are. So in this case, it's like the size of this shape, and then maybe there are also different orientations or different shapes that you can see. And let's just have the model directly predict that underlying factor of variation. So in this case, the size of this object. And let's see if the model then can generalize. And for the most part, this paper had quite a bit of negative results. So, you know, sometimes it worked, but it did not work very well in general. And especially, that was especially true when you're looking at things like extrapolation and composition. And so I think there's kind of a lot of evidence at this point that neural networks don't do a great job of extrapolating and don't automatically learn things that compose well. They don't generalize in this compositional systematic way by default, as well as we might have hoped. But I think this paper really crystallized that in a nice way. And so, oops, forget about that stuff in the background. So, you know, this is kind of the situation that we're in right now. This is a great webcomic, XKCD. You know, you can sort of, if you want to be uncharitable, say all of this deep learning and all of the really, you know, impressive stuff that's happened in the last 10 years, we're kind of just, you know, stirring around this big pile of linear algebra. We have no idea what we're actually doing. It might look like it's working, but just, you know, it just looks that way. Maybe it isn't actually working at all. And, you know, that's kind of obviously a big problem for the safety of these systems. If they're not reliable, if we don't really know how they work and whatnot, then we should naturally be a little bit concerned about using them in high stakes applications, like for instance, self-driving cars. And so AI safety has been, I would say, this phrase and sort of discussions about this have been a pretty big deal in AI since shortly after I got into the field in 2012, which I was very happy about because, you know, I thought this was kind of an obvious concern before I got into the field, and it seemed like it wasn't getting enough attention. And people often talk about like these two different kinds of AI safety. And so there's kind of like, make the current machine learning systems more reliable. This is sometimes called like short-term or near-term safety. And that's contrasted with like the long-term safety of like, what happens when we have really advanced AI systems that are maybe like super intelligent, much smarter than people, and are they going to sort of take over the world and not really leave a space for humans anymore? And I mean, I think this distinction is like sometimes valuable. I really don't like framing it this way. I think it's not really about short-term and long-term. It's more about like, is this an AI that is still relatively crude, like a lot of AI techniques are, or I'd say arguably everything that we're doing right now is still crude in the sense that it doesn't embody artificial intelligence as it's sort of depicted in the popular imagination and science fiction. So even you know, Gato and GPT-3 and whatever, all the most general models that we are seeing today are still relatively narrow and still have clear flaws, like along the lines of what I was showing you with this failures of systematic generalization. And so, but basically you can talk about like, are we worried about the AI being too stupid or too smart? And I think, like I said, that distinction is sometimes useful. Overall, I think it's not incredibly useful. And that's because I think actually a lot of the same problems crop up in either case. So, but I will say that ultimately there is some important differences when you start thinking about more advanced AI systems and thinking about how we can actually make those systems safe. The sort of the bar goes up quite a bit in terms of what you need to do and the kind of problems you need to worry about. But it's important to note that, like, right now we already have seen all sorts of reasons to be concerned about AI systems going wrong in the present. So this is a classic example from, I guess, 2016 of a Twitter bot trained by some folks at Microsoft. And this was just sort of unleashed on the actual Twitter, and within a day, I think largely due to the actions of various trolls, it had gone, full racist Nazi on the world, and they shut it down and took it offline. And that's kind of like a toy example where, you could say that certainly might have offended some people, but it maybe wasn't, a huge disaster or anything. On the other hand, there's a few examples that I want to give that I think are much more concerning. So when we look at the use of predictive policing, we see that, like, AI is being used in predictive policing and actually in a lot of other areas of law enforcement. And a lot of people have been really critical of this because of its potential to reinforce existing biases such as racism. So when you deploy a predictive policing system and you train it on data that is about arrests, and you treat arrests as if they are representative of the amount of crime, you are opening up the possibility to create a self-fulfilling prophecy where, you police an area more because you expect there to be more crime, and therefore the police are more present and witness more crime, arrest more people. That doesn't actually mean that there was more crime there in the first place, because you have this massive confounder of there being more police there to detect the crime, and them, maybe being more primed to view activity as criminal. And we also have this issue, like, it's non-trivial to make systems that are fair and don't discriminate on things like race. And in fact, there's a whole, massive amount of research that is going into fairness of AI systems to try and deal with these kinds of problems. And there's kind of some fundamental ambiguity in terms of what it actually means for a system to be fair. So pretty good, pretty reasonable in isolation, but it turns out that they're sort of mutually incompatible in general. And I think my take on this, and I think a lot of people who are, like, looking at this seriously from a social perspective as opposed to just purely a technical perspective, is that a lot of these social issues of deploying AI systems are not things that can be defined away or fixed, with technical fixes. It's really a complicated question. Like, the issue of fairness and bias is ultimately, I don't think, something that we're going to reduce to a simple formula or definition. And it's really something where we need to just be much more conscious of how we use these systems, how they're being deployed, and we need to have, a rich, like, sort of framework for oversight and responsibility of the people developing and deploying the systems. Just one more example of, like, existing risks or even harms of AI systems is this flash crash in 2010, where we saw about 10% of the value of the stock market sort of disappear, and then most of it come back within the course of, a few hours or even a few minutes. And so these incidents that I just discussed share a lot of like, common features that I want to highlight. So one of these is the lack of meaningful human control. And in this case, it's because the time scale was so fast that it was difficult for people to intervene. And in fact, ultimately, I believe they just shut down the stock market, and now they have, like, sort of a switch to just stop trading at any point in all the stock exchanges for this sort of thing. excuse me. And another thing I want to highlight is sort of the lack of understanding or interpretability. So we're deploying these systems without necessarily understanding exactly how they work or why we should even expect them to work. And then, we don't really know what's going wrong when it goes wrong. And then I guess finally, there's sort of a maybe a lack of like nuance or attention to the goals of the system. So in the case of the predictive policing, it's like you might just say, oh, I want to like make accurate predictions, but you can make accurate predictions by making self-fulfilling prophecies. Like that's a perfectly acceptable way to achieve high predictive accuracy according to most machine learning systems. And similarly, like if you're deploying AI systems in finance, there's a lot of ways that you could manipulate the market in order to make money, and it might be difficult to rule out all of those forms of market manipulation. And then finally, maybe I already said finally, but finally, loops. So in all three examples, there was sort of a feedback loop. We had the Twitter bot feeding back with the other people on the internet and sort of creating this reinforcing of the racist behavior of the Twitter bot. In the predictive policing, you might, go start policing an area more heavily, make more arrests, be like, oh wow, there's a lot of crime here. We really, need to put more cops there, and then you see even more arrests. And the flash crash, I think, was largely caused by different trading algorithms sort of feeding off each other and driving the price down very quickly because of some way that they were sort of setting their prices based on the prices of the other systems. And concretely, because I don't know the details of this one, but concretely I know there are examples on like Amazon or other online sales platforms where the price of some items just skyrockets because there are sellers that will just automatically try and sell it for like a few pennies more, 1% more than whatever the highest cost is right now. And if you have two of those going, then they just ratchet up the price. So sort of coming back to this theme of like the two kinds of AI safety and the short-term versus long-term, if you take a very broad definition of AI safety, I think it encompasses actually quite a bit of what is going on in the field right now. And you'll see that once I start talking about the specific research areas a little bit later in the session. On the other hand, if you just focus on this long-term safety, this is still like quite a small community. And so arguably like an order of magnitude or even less than are working on safety in a more broad sense. And I think that's actually kind of surprising if you look at this from a historical point of view, because the stakes of losing control over AI systems, not just in some isolated incident like this, but globally and in general for the entire future, are incredibly high. And this is something that pioneers of the field recognized and were aware of. So we have these quotes from Alan Turing and Norbert Wiener that are very just kind of stating very clearly the idea that machines are liable to take control, and if we aren't very careful about how we program the purpose of these machines, then that might be a terrible thing. But the discussion of this concern and work on it in the field of machine learning and AI is really quite recent, and the recent interest in it actually, I would say, to some extent emerged outside of the AI community originally with people like Nick Bostrom and Eliezer Yudkowsky. Nick Bostrom is a philosopher at Oxford who wrote that book, Superintelligence, which I'm sure many of you have heard of. And Eliezer Yudkowsky is basically an internet blogger. So yeah, and looking like, so Eliezer and Nick were talking about this, I guess 20, 25 years ago, something like this. And it's only really in the last, like, let's say 6 years that this has finally kind of worked its way back into the research community. So 2012 is when AlexNet happened, and around when I joined the field. And so that was like when deep learning was blowing up. And we didn't see, so really, I think a lot of people in the field were not even aware of this concern at that time, which I was really surprised by, because I had assumed that people in the field sort of had really great reasons to not be worrying about this. And 2014, I think, is when the discussion really began about AI safety, and in particular existential risk in the AI community. And yeah, so this term, I think sort of seminal moments in here are like the publication of Superintelligence and this paper Concrete Problems in AI Safety, which I think really sort of legitimized this problem in the eyes of a lot of people, because it said, look, this is a technical research problem that you can make technical research progress on. And again, highlighted a lot of the similarities in terms of near-term and short-term safety, or like, as they're so called. And 2016 is also when this term AI alignment was actually introduced. And I think only now, like, are we starting to see, though, this really going mainstream. So we're actually starting to see like a lot of big companies who I think are not in this small community of 100 or so researchers are starting to use this terminology and be more willing to talk about these kinds of problems. And I think a lot of that is driven by the recent progress of really large deep learning systems, so-called foundation models such as GPT-3. So I think actually this is really like a sea change moment. And it reminds me a lot of what the field looked like back when I started in 2012. And back then, deep learning was still viewed as sort of, I want to say, kind of out there or overhyped. A lot of people were skeptical that it was just kind of a cheap parlor trick or something. And what we saw in terms of progress, I think, was really, really remarkable. And it kind of took over the whole field. And happen with AI alignment. This is what I foresee happening in the next 5 or 10 years. And the reason is basically this. As like the data and compute and parameters of models scale up, I think the limiting factor is going to become how much information can we provide these systems about what we actually want them to do. So like how much human labor can we put into building these systems? And a simple plot like this basically captures the point. The amount of human labor that we have available to us grows much slower than the amount of compute or the amount of compute resources. So yeah, and why is alignment and foundation models, why do these things go together actually? So here's an example that I think is really illuminating and gives a sense of like what I mean by alignment. So I'm going to talk about that more in the next session, but just to sort of preview it right now. This is an example of GPT-3 from GPT-3, and if you prompt it with this question, which is a nonsense question, Sporgle and Morgellard made up words, you get a nonsense answer. On the other hand, if you include this prompt and just a few examples of like what's normal and what is nonsense questions, then you can get it to instead recognize nonsense questions and say, yo, be real, instead of answering them as if they were real questions. So this means that GPT-3 had the ability to tell the difference between these two things. It just didn't really want to, or it wasn't trying to in some sense. And so the goal of the system was not correct. And so the issue was not the capabilities of the system. It actually had the capability that we wanted. The issue was that we hadn't aligned it in the sense of we hadn't made sure that its behavior was aligned with our preferences. And I think when we look at these models, alignment is going to be the main challenge in terms of getting them to do things that we want. And I know this is a little bit at odds with what I said at the beginning of the talk about these fundamental limitations of deep learning systems, but I want to say that I actually expect, and I think this is, I'm not very confident about this, but I expect that we will be able to overcome those limitations through some clever combination of deep learning and other methods in AI, and the kind of engineering hacks that we have seen, making progress or driving progress in deep learning and AI over the last 10 years, including, things like new architectures and new optimizers, new activation functions. So that's kind of the background framing. Now I want to tell you, like, when we talk about AI safety as a technical problem, what does AI safety research really look like? And how can we think about how to make AI systems safer? And there's a lot of different sort of research agendas about this, including this paper, Concrete Problems in AI Safety, that I mentioned, maybe most famously. But and a lot of the times these sort of have the flavor of an agenda that breaks down the problem into different subproblems. My favorite of these so far is this breakdown from DeepMind into just 3 categories: specification, robustness, and assurance. And so the rest of this part of the talk, I'm just going to walk through these 3 categories of problems and give you a little bit of a flavor of like what the problem is and what kind of research is being done there. So I'll start with robustness, which is also sort of how I started the talk. And despite all of this impressive progress, in a way, progress is going slower than people were thinking it might, 5 or so years ago. So in particular, self-driving cars, sort of one of the classic safety problems, were really, people thought that we might have self-driving cars by now. And I guess, basically, there's been a failure to deliver on that. And I think this is largely because of safety problems, and in particular, the problem of robustness. So one of the key problems for self-driving cars is distributional shift. And it's, you can train cars to do well on like the streets of Palo Alto or New Mexico, but that doesn't mean that they're going to be able to handle like a snowy road in New York City. And so while we have seen self-driving cars deployed in some of these more sort of easy settings, they really are not being deployed, nearly as widely as people thought, because as it turns out, models are really sensitive to this kind of distributional shift. So to say a little bit more about this, there's a couple experimental results that I think really highlight just how severe this problem is. So here is one of those examples, which is an attempt to replicate the test set from ImageNet and CFAR10. And so these authors tried to collect data in exactly the same way as it was collected when these data sets were originally created. And they found that despite doing their absolute best effort to gather data from the exact same distribution, there was still enough distributional shift to lead to something like a 10% drop in accuracy. And so this was kind of like the closest to the same distribution that you can imagine getting, and yet we still have this significant gap in accuracy. Another example of just how sort of sensitive neural networks can be is this paper, where you can change the initialization of a neural network by 1 bit, just 1 bit. And in fact, it doesn't even have to be a significant bit. It can be the trailing bit, the last, smallest level of numerical precision. And just that one change, because of the instability and sort of chaotic dynamics of the training of neural networks, it's as if you had completely initialized the model completely differently, and trained on like the data in a different order, and just all of the different sources of randomness that we know contribute to different results when we run different training runs. These are all, roughly, as bad as just, you get as much randomness from just flipping this 1 bit. And so there's sort of more, flavors of robustness research than just these 3, but these are kind of, I think, the biggest threads of research right now. And so I just want to highlight these different, subfields of research. We have adversarial robustness, which I already talked about a little bit. Non-adversarial robustness, which is, arguably more realistic for most of the kinds of problems that we want to solve. And so this is an example from a data set created by Dan Hendricks, an AI safety researcher, trying to sort of imitate the kind of image corruptions that you might actually see in practice. And then finally, sort of the most recent, so this is also in chronological order, interestingly enough, the most recent thread of research in this area is invariant prediction, which is also sometimes called out of distribution generalization. And here, it's really about sort of the flavor of research there is saying, well, look, there's all these different features that the model can pay attention to when it's trying to make predictions, and we want to make sure that it's only paying attention to the right features, the ones that are going to actually be useful for predicting in many different contexts. So classic example here is cows on the beach, and there's this paper by Sarah Beery and others that shows that image classifiers can really fail to recognize cows on the beach because they're so used to seeing pictures of cows against a grassy background. And so the change in the background confuses the model because the model didn't actually learn just about the cow. It sort of learned to detect cows by a combination of the features of the cow and the features of the background. So I'm just gonna like really briefly summarize some of the results in these areas. So adversarial robustness, one of the most important things to note here is that this is not just, you know, a matter of making these perturbations on the computer. People have shown that you can actually create such examples in the real world. And so you can print out this sticker and put it on a table next to a banana and take a photo of that and make your classifier think that it's a toaster instead of a banana. Overall, adversarial robustness is and continues to be a massive research area. And there's a few general findings. Basically, the attacks, the adversarial attacks, generalize across different models. And black box attacks work quite well. You don't even need to know which model you're attacking. And defenses don't work very well unless the attacker doesn't anticipate you using that defense. So a lot of defenses have sort of been shown to be some form of security by obscurity. And I think, you know, there is some progress being made in terms of making more adversarially robust models, but it's been remarkably slow compared to, I think, you know, when I was talking to people when the original paper that Panda Gibbon images from came out, I think the default expectation was that this was just a quirk of how they trained that particular model, or it would be solved very easily by like making the model generative model or something like that. I think about a year after that, Ian Goodfellow came out with a paper saying, no, actually a lot of these simple fixes don't seem to work, so maybe we actually need to do some research on that. But you know, even he was not expecting it to be nearly as hard of a problem as it has turned out to be. So maybe we should be focusing on like a simpler problem, like non-adversarial robustness. And again, just to sort of summarize my understanding of the progress there and the state of that field, generally speaking, models are getting better, and getting better also leads them to be more robust. However, most of these improvements are sort of orthogonal, so they aren't getting more robust in particular. It just happens that as the model gets better, it also gets more robust, which is actually really good news. But it does mean that you have to be a little bit careful if you are trying to build a method that specifically improves robustness as opposed to just improving performance and then sort of improving robustness as a side effect. So again, going back to Dan Hendricks, in his writing about AI safety, he's talked about this idea of trying to have minimal capabilities externalities. So if we really want to have a method that is about improving the robustness or improving the safety, we should make sure that it's specifically improving safety, in this case, the ability to detect anomalies, as opposed to just improving accuracy and sort of as a side effect, improving anomaly detection. And that's important because we know that scaling does tend to improve these metrics in a fairly predictable way. Finally, this idea of invariant prediction, you can think of this as about trying to avoid shortcuts. So the background feature is like a shortcut way of predicting the class, which is maybe simpler than actually looking at and understanding the foreground and the details of the different kinds of objects or animals. And one of the really interesting things here is that you can view this whole problem as being fundamentally about underspecification, in the sense that we didn't tell the model which features to pay attention to. And so this problem of robustness, where it's looking at the wrong features, is actually, to some extent, also just an issue where we didn't say enough about what we wanted from the model. And I guess I'll skip over this example in the interest of time, but you can actually view adversarial examples in the same light, as resulting from features that are actually predictive. And the issue is just that we need to say more about not just what we want the model to do, but how we want it to do that, how we want it to do that. So not just say get good performance on this data distribution, but also do it by using the right features, the features that we care about. Yeah, so what happened there? So the next, that brings me to the next topic, which is like specification. So specification, again, is about defining the purpose of the system, or the goal, what we want it to accomplish. And so here's like maybe the most famous example of a specification failure is this boat racing game, where the goal that we have in mind for this is for the boat to race around the track, but because of the way that the scoring system works, it gets extra points for collecting these power-ups, and so it just goes in a circle collecting those power-ups instead of actually completing the race. So in general, specifying what we want can be difficult. Whoops, I just exited the slideshow. Why did I do that? Here we go. And I think it's easy to see how this becomes a problem when you start thinking about like real-world tasks like cutting hair or braiding hair, basically any robotics task. It's quite difficult to define success or failure when with a reward function in terms of like, the joints of the robot and stuff like that. And so most of the work in this area these days is about ways of learning the specification as opposed to having to write it down by hand. So here are a few different examples, and I'm going to talk about each of these briefly in the next few slides. So one of the classic and one of the simplest ways you can think about learning what to do, like what kind of behavior the system should have, is just by imitating human behavior. So imitation learning. So one of the classic papers here is called Dagger, and they point out one of the basic issues with doing imitation in sort of the most naive way, which is behavioral cloning, which is that your errors can compound. So when you're actually taking decisions in a dynamic environment, even if you're making like reasonably good predictions at any given time step, every failure, every bit of error in the prediction can sort of multiply. And so you can end up with the trajectory of your agent being very different from the trajectory that you're trying to imitate, or the trajectory that a human would take. So for instance, the car can go off the track. And in this work, they said, well, let's just correct that by having human look at those instances and say what to do, even when the car gets further away out from what it originally was doing in training. So a way that you might try to address that problem is by instead learning what a human is trying to do based on watching human behavior. So trying to infer what the goal or reward function of a human is. And this is also, led to some really successful work in the past, doing things like flying toy helicopters really well. The key difference here from imitation learning, another one of the key differences, is that if we learn what the human's goal is instead of just learning to imitate them, then we should be able to accomplish that goal more efficiently than the human could. On the other hand, in practice, this can be very tricky because imitation learning and inverse reinforcement learning don't look that different in practice. We still have to somehow infer the goal, and there aren't methods that are much more that do, like, in order to do a significantly better job than imitation learning, you have to sort of model the human and understand why they're making mistakes. Otherwise, you just assume that whatever they're doing is the best way to accomplish their goal, and then you're back to doing imitation learning. One more important method here is cooperative inverse reinforcement learning. And so this is a fairly recent paper that sort of came out of the AI safety community. And the idea here is that instead of just thinking about learning the human goal from human behavior, we should think about the human and the robot collaborating to maximize the human's reward. I think the most important insight here is that we should treat the human's reward, the human's goal, as something unobserved, something that the agent has to sort of try and learn through interaction with the human while also trying to optimize. And this leads to naturally to a lot of good sort of incentives if you can actually set this up right, which in practice might be somewhat intractable. So one of my students, Dmitry Krasnendikov, did some follow-up work sort of showing all of the benefits that you can get from setting up the problem in this way. But I think the most popular method, and the one that I'm most excited about nowadays, at least most popular within the AI safety community, is reward modeling, which is learning from explicit human feedback about human preferences. So instead of just trying to learn from human behavior, for instance, human demonstrations and assuming that they're optimal, instead, we just have the human giving feedback saying which behaviors they prefer. So in this famous paper from people at OpenAI and others, they trained this hopper to do a backflip using this method, which was something that was quite challenging to do using a hand-specified reward function, and probably would be even harder to do if you were trying to manually control this thing yourself. So the point was, we can train these agents to do things that we can't demonstrate ourselves and that we can't write down reward functions for if we learn a reward function from human feedback. And the way that that works is you just show a person an example of two different behaviors and ask which one they prefer, and you assume that they prefer the one that has higher reward and learn a reward predictor that is consistent with that human feedback data. Yeah, so getting close to the end here, I will maybe, because I want to have some time for questions, and I think I have about 10 minutes left in total. So yeah, I'll try and go even a little bit faster through this one. So assurance is the last part of this breakdown. And assurance is really about, like, how can we have trust in the system? How can we trust that it's going to do the right thing? So we know that systems are sometimes not robust, so they can generalize in weird, unexpected ways, and that can cause failures. And we know that specifications are hard to get right. So it might be that, you know, we didn't specify the problem correctly, even though we tried our best. And so we'd like to understand, like, how the system that we build works, or at least how the learning process that creates that system works. And this is particularly challenging, I would say, with deep learning and with big models in general, which is unfortunate because we know that these systems are sort of the driving progress in AI right now. So there's a few different approaches to trying to understand, like, how these systems work, how deep learning works. One thing is just try and visualize what's going on. You can also come up with different theories about what's going on and then try and test them using a sort of like behavioral neuroscience approach, or empirical theory, it's sometimes also called. And you can also, like, just do more traditional mathematical theory. So I'll just run through a few examples really quick. This is one of the classic results that showed actually a lot, like, traditional learning theory was just not going to allow us to explain the generalization of neural nets because they can fit random labels perfectly. And that means that they have a large effective capacity, and therefore it's not just a matter of, like, them having a restricted capacity that allows them to generalize, which is sort of how this has traditionally been understood in learning theory. So since that work, there was some work, you know, this is the first example, I think, that was say, look, we can prove that if we train this model, it will get more than 0% accuracy on a test set. And they did this using some measure of information gain. So saying, look, when we train this model, we can show that it actually hasn't moved that far from the initialization, basically. There's also been work trying to sort of explain neural nets in terms of more well-understood models like kernel methods, and sort of reduce them to, let's say, a kernel method with a particular kind of kernel. But I'm not very convinced by that line of work personally, although I also haven't studied it very much. And that's because I think it doesn't do a good job of accounting for the representation learning component of deep learning, which I think is really, the key thing that drives that makes it powerful. And so sort of an alternative explanation that is my favorite explanation so far is basically saying, look, neural networks are nothing fancy, but the one like extra bit of magic that they have is that they are able to learn the data manifold. And when the data manifold is much lower dimensional than the original input data dimension, then doing some more brute force approach on that lower dimensional manifold can lead you to be exponentially more efficient. And this explains this power law scaling that has been observed. So these are sort of approaches to explaining the learning behavior of neural networks. When we also might want to explain the behavior of a particular network after it's been learned. And approaches there include like feature visualization. So trying to look at what sort of inputs maximally activate different features. And so can we see like, this kind of looks like it's paying attention to flowers. Maybe this is a flower detector. Things in the lower levels tend to look like edge detectors, but then as we move up the network, it maybe gets harder to interpret them. And so Chris Olah has done a lot of work like this. And then there's also a lot of work on saliency maps, which is basically saying which part of the input was relevant for this prediction. Unfortunately, there's also been a lot of work showing that most of these saliency map methods are very unreliable themselves and really questioning their utility.